Today we're gonna go back to this Clyman-Winston's basic graph container lemma. I would like to mention two more applications of this on counting type of problems. So one of which is in their original paper when they came up with this Clyman-Winston's graph container lemma, in which they count the number of C4 free graphs. So this is one of the things we will be looking at. So let's start with the first application, one more application. Lecture 12. The first application is related to what we have seen earlier. Remember, I left as an exercise to use Clyman-Winston's graph container theorem to bound the number of independent sets in regular graphs when the average degree is growing sufficiently large. So recall that the theorem that we proved, let me write it down. Yes, so this theorem says there for some for any n vertex the irregular graph G, the number of independent sets is at most 2 to the 1 plus, I just write the easier version without specifying the little o1 term. The little o1 term is like growing to 0 polynomially in D. We proved it before. What's more important is the leading term is n over 2 when D is sufficiently large. So this guy goes to 0 as D goes to infinity. Now in this result, this is optimal as we remarked before. N over 2 in the power is optimal as one can consider bipartite graph G. In this case, the independence number is at least half of the vertices. And by taking all subset of the largest independent sets, you immediately get I of G is at least 2 to the alpha of G. Okay? So 2 to the n over 2, this leading term cannot be improved. Now, as I keep trying to repeat that whenever we see a theorem, that's not the end of the story. When we understand the proof, we should also try to ask questions when we see a statement. So here, when we were told that this 2 to the n over 2 leading term is optimal, the obstruction is because we can improve it because of bipartite graphs G. For bipartite graphs, this is tight. So naturally, one can ask if this regular graph, when the degree is growing, if this graph is not bipartite, it's very far from bipartite, then is it possible to improve this bound? Ideally, improve it exponentially, like in this constant. And turns out this is the case. We can do that. So let me write it down. So a natural question is, can we improve this bound when G is far from bipartite. Of course, we have to make this far from bipartite rigorous. What do we mean by far from bipartite? Okay. Here, we're going to present the results where which answers this question in the positive, and then how we measure that a graph is far from bipartite is through the eigenvalue of a graph. So let's recall, when we talk about eigenvalues, we are actually meaning the eigenvalue of its adjacency matrix. So again, recall for graph G, let's say m vertex, the adjacency matrix A. Usually I should specify this is adjacency matrix for graph G, but let me omit the subscript G. This is basically a m by n matrix, m by n 0, 1 matrix. 0, 1 matrix where each row and column represents the vertex sets, the vertices in the vertex sets, and at the ij's entry, you put 0 or 1, depending on whether I and vertex j is adjacent or not. Okay. So the entry, the ij's entry equals to the indicator function of whether vi is adjacent to vj. Okay, so for this matrix, its eigenvalue, we call it the eigenvalues of G. It's well known. Maybe I'll leave it as exercise. So to show that for D regular graphs, if we list the eigenvalue of G in decreasing order, then lambda for D regular graphs, lambda 1 is D. Exercise 1. Exercise 2, for D regular bipartite graphs, then we have lambda 1 is D, and the smallest eigenvalue is negative D. Okay. So the way we're gonna measure whether a graph is far from bipartite, from these two exercises, we know if G is a D-regular bipartite graph, then its first eigenvalue is D and the smallest eigenvalue is negative D. So if we say a graph is far from bipartite when lambda n is bounded away from negative D, let's say negative D plus some constant times D. This I will consider it as far from D. Okay. So this is how we measure it. Let me. So let me now state a theorem originally proved by Alon and Rudolph for multicolor Ramsey results. So here's a now we consider so we consider D-regular graphs with smallest eigenvalue lambda n bounded away from larger than negative D. Okay. Much larger And this is what we mean by far from bipartite. This is one way of saying a graph is far from bipartite. In this setting, along with Rödel theorem, in early 2000, they proved that if we have, okay, so for any epsilon bigger than 0, there exists an epsilon constant C such that the following holds. So for any m vertex irregular graph G with the smallest eigenvalue, lambda n of G, to be at least negative lambda for some lambda. So I assume lambda is a positive value, which is strictly smaller than d. So this is larger than negative d. Then we have the number of independent sets, the number of independent sets of size m, then for any, let me do it this way. The number of independent sets of size little m, we can get an even finer control on every slice. So this is number of independent sets of size m is at most this value, lambda over d plus lambda plus epsilon times n divided, choose m. So first, I will leave it as an exercise for you to show that this finer estimate, first of all, this theorem implies this bound that we have above. Okay. So this is a stronger theorem. All we need to do is saying that for any d-regular graph, we know now lambda 1 is at least d, lambda n is actually at least negative d with equality when the graph is bipartite. So just use the fact that lambda is at most d, plug in here, you can derive this one. So I will leave as exercise. Use the above theorem to derive heart, where the heart is this guy. All right. But we can do better, because when the graph is, as I said, far from bipartite. So when the graph is far from bipartite, lambda is strictly smaller than d, let's say 0.99 d. Now if you look at this value, then this is strictly less than 1/2. It's like 1/2 minus some small constant delta. So you take epsilon sufficiently small, you will get that this whole coefficient in the front is strictly less than 1/2. Okay. Is that correct? Yes, right? So you have something strictly less than 1/2, choose m. sum over all m. I think this is already less than this number, no? 2 to this. Sum over n choose I equals to 2 to the n. All powers set of yes. So we gain exponentially from this bound if lambda is bounded away from D. Okay. So let me write it down. When lambda is bounded away from D, so for example, D minus some delta D, let me just write this omega D, then we get I of G m is less than 1/2 minus some constant times n, choose m. We get I of G is at most 2 to the n over 2 minus some constant times n. Okay. How do we prove this? So if the proof of this idea is simple, the original proof use spectral method, but here we're going to use Kleiman-Winston. Before proving it, let me mention some remark about this theorem. First of all, this coefficient here is optimal. We cannot hope to have any smaller constant in front of n here. So let me cut it so we can see it. Let me make the remark. So remark, the constant, the first remark, the constant lambda over d plus lambda is optimal. This is because we have Hoffman's theorem. Let me remind you Hoffman's theorem. If you don't know it, just take it for granted. Hoffman's theorem says, Hoffman's bound says, if you have a deregular n-vertex graph, G, then we have the independence number of the graph is at most negative lambda n of G, the smallest eigenvalue, divided by D minus the smallest eigenvalue of G times n. And remember, I actually write lambda n as negative lambda. I take the absolute value, flip it to positive. So this is a negative number. So this is the lambda here. This is the d plus lambda down here. So Hoffman's bound, the point is the Hoffman's bound equality holds sometimes. It does hold. So there are graphs where the independence number is this guy times n. Then of course you take the largest independent set of this size and you choose all m subset of it. This equality could hold. So I mean could hold up to this epsilon. So we cannot replace this by anything smaller. Second remark is that so what else we can remark on? Look, obviously we should remark on this constant, and also why only from m is at least some large constants times n over d. This is also optimal up to the constant c. So the range for m is also best possible up to the constant C. This is because if we take epsilon small, consider a small epsilon bigger than 0. And now let's consider independent set of size m that's at most size, let's say epsilon n over d plus 1, let's say. So it's roughly epsilon n over d. So we are constant factor smaller than this threshold, the requirement. I'm going to prove you that this bound is not true anymore. So first of all, for bipartite graphs, this is strictly less than 1/2. For non-bipartite graphs, there's a remark up here. So if m is smaller than this, what we can do is we just greedily, so this is our graph G, you greedily pick, I claim that I of Gm, the number of independent set of size m, is at least 1 minus epsilon times m, n, choose m. And obviously, this is larger than this guy. I mean, this is at most 1/2 times n, right? 1/2 times n. But here we have almost 1 times n, choose m, larger than that. So when m is smaller, not true. And why is this correct? This is because we can just greedily pick things. And we can always do that. If you pick a vertex v1, and then you remove its neighbor, which is of size d, remove, okay? Remove. You can pick whatever v1 you want, remove. Now you pick whatever v2 you want, you remove its neighbor. Then v1, v2, of course, in this way, it's an independent set because every time I remove the neighborhood of the previous vertex, dot, 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 up until you choose vm, you remove, right? Now, what's the total number of vertices that we removed? Total number of vertices involved is at most, we have m rounds. Every round, we pick out a vertex vi, we delete its neighborhood, which is d vertices. So it's m times d plus 1, which is at most epsilon n. In other words, there are at least 1 minus epsilon n here. So before we pick out m vertices, every time we have at least this many vertices to pick out the next vertex. So you you always have, you just greedily have this many choices for the first m choice vertices. Okay. Maybe I mentioned that here lambda n is at least negative d. Okay. Good. This is the two remark I want to make. Anything I want to say more? No. Okay, so let's prove it. The idea is simple, 2 sentences. To use Kleiman-Winston, the key thing is we need to prove this graph G is locally dense. In other words, supersaturation. And here we are given what? Read the statement. we are given the eigenvalue spectral information of G. So when we have spectral information of G and someone talk about supersaturation, then the first thing that should come into our mind is the theorem that we mentioned earlier a few weeks ago, expander mixing lemma. And the one we can use, for example, you can use Alain Cheng's expander mixing lemma that I mentioned before. So the idea of the proof use expander mixing for supersaturation or locally dense. And then you can use Kleiman-Winston graph container theorem. This is it. So let's see some details. Let me remind you this expander mixing. This part I will remind you fairly quick. Expander mixing along Cheng. It says that for any m vertex be regular graph G, and you take any subset S in V of G, then we have the number of edges. The number of edges of G on S is at least 1/2 times D over N. D over N S squared over 2. This is the expectation, sort of, if the graph is random, plus lambda. I think not. Lambda means the smallest eigenvalue, I think. One second. Yes, so lambda n of G. Okay. Now, using this, I will not prove this. You can prove the supersaturation. Now we can prove along Rödel. This theorem here. So let's I will tell you how to choose parameters. We're gonna let R to be lambda over D plus lambda plus epsilon over 2, leave a little room, times N. So the bound, remember, the bound we want to prove in this case would be IgM is at most this R plus R is this guy plus epsilon N over 2, choose M, okay? So the bound we want to prove, we want IgM is at most R plus epsilon N over 2, choose M. This is what we want. And we're going to use this capital R and this beta to be epsilon D over N I'll tell you what is Q as well. Log 2 over epsilon times N over D for the fingerprint size. And we're gonna first use a long chain to prove locally denseness or expander mixing, showing that for any sets S of size at least R, this quantity here, when you go above the Hoffman's bound, we see lots of edges. Then we have EG of S is at least beta that we just defined times S choose 2 locally denseness. Okay, this is pure calculation. I will skip it. Now, when we have the locally denseness, then Kleiman-Winston implies that the for any M at least Q, we have I, G, M is at most N choose Q, choose the number of fingerprints, size Q, and remaining sets is of size R, the available remaining set string to R after Q steps. We have to choose Q vertices in independent sets are chosen. There are M minus Q left. So M minus Q. This is the Kleiman-Winston. So all we need to do now is to bound. Let me do some calculation. R plus epsilon N over 2, choose M. Okay. Oops. What did I do? This is our goal. All right, so let's simplify things a little bit. There's a nice trick of bounding this kind of thing. This trick is to use telescope products. So if we let this guy define it to be, this is a nice trick. Define this product of these two binomial coefficient by consider this is N, R, M are fixed, and consider Q as variable. So let's define this to be a function of Q, FQ. In this way, what is F 0, for example? F0 is N choose 0 times R choose M minus 0, right? This is just R choose M. N choose 0 is 1. Then, what is in this way, IgM is at most f of q. But what is f of q? We can write it as f of q over f of q minus 1 times fq minus 1 over f of q minus 2 dot 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 f of 1 divided by f of 0 times f of 0, right? So this is just write it slowly. Products I goes from, oh not I, let me use J maybe. K goes from 0 to q minus 1 f of k or k plus 1 over f of k times f of 0. Don't forget the last term. Now, let's look at what's this guy. Now, this guy equals to, let me do some calculation for you, m minus k over k plus 1 times m minus k over r minus m plus k plus 1, pure calculation. There's some calculation, blah, blah, blah. This is smaller than 2m over epsilon k plus 1. Anyway, we have one fixed bound like this, one bound to bound this. Now multiply them together, we have, this is at most. We take the products q times, so this is 2m to the q, epsilon to the q. So we have 2m over epsilon to the q. And then at the bottom, we have k plus 1. K plus 1, so it's from 1 to q, basically, k plus 1. So it's q factorial times 1 over q factorial. F of 0, we know what it is. F of 0 is r choose m times r choose m. Let's write this one more time. Elementary estimate, k factorial is at least k over e to the k. So let's do it for q factorial. We have, this is at most. Put everything together, 2em over epsilon q to the q, using this inequality. Multiply by r choose m. Okay. And remember, we want to compare this guy to r plus epsilon n over 2 choose m. This is what we want to compare. Let's use another inequality. When we compare these two, this looks the same. This slightly smaller than that. So there's an inequality says for any a bigger than b bigger than c, at least 0, a to c times b over a to c is at least b to c. So think of a as this guy, slightly larger. B is this guy, slightly smaller. C is this guy here. We have, this is at most what is the number? Let's write this vector. Now use this inequality, we get r over, this is b over a, r plus epsilon over 2 to the power m times the factor that we want. So now all we need to do is to prove this guy is less than 1. Okay, then we are done. That's basically pure computation. The rest I will skip it. Okay. Any question? I show some like this kind of telescope product trick, but if you filter out the calculation, the idea just 2 sentences. Use this expander mixing to get supersaturation. Once you have supersaturation, you can apply Kleiman-Winston with the correct parameter. So you might wonder, how do you choose these choices? So this you have to try to do the calculation yourself to get a feeling of how to fix these parameters. There's no trick. So this is the first part. The one more application, which is an extension of discounting independent sets in regular graphs when the graph is bounded away from bipartite. Now let's see the original application of Kleiman-Winston on counting C4 free graphs. labeled. We always mention labeled C4 free graphs on vertex set n. So let's recall how large can the C4 free graphs be? Number of edges. So Kovalyov-Turan and later maybe, yes, Kovary, what's the accents here? AST and also construction by Brown basically shows that the extremal number, maximum number of edges in the C4 n vertex C4 free graph is 1/2 plus little o1. More accurate exact number for certain values of n will also determined by Zoltan-Furedi. But let's just look at this asymptotic one. It's 1/2 plus some error term times n to the 3/2. Now, if we so let's look at the number of C4 free graphs. So if we let f of, let's denote by fn of C4 to be the number of labeled C4 free graphs on n. Trivially, then we have fC4. fnC4 is at least 2 to the extremal number of C4. Take the largest one, take all its subsets, which is at most, we know the largest such graph can only have this many edges. So we can always choose this upper bound is bounded by, if let's say your C4 free graph has m edges, the number of edges is between 0 and extremal number of C4. So, and you have totally n choose 2 labeled edges to pick m of them. If you do this calculation, m is very tiny. This is far away from the middle of this term. It's subquadratic, so which means the last term is the heaviest one. Just multiply by 2, we will already get the upper bound. So this is roughly 2 to the, is roughly the last term. So the last term is n squared, roughly choose n to the 3/2. Choose this guy. If you write it in the exponential form, this is 2 to the some constant times exn C4 times log n. So you see the upper and lower bound, there is a log n term here, different in the power. Okay, so Kleiman and Winston's original application of their graph container is to remove this log n, to prove that to determine f of n, fn of C4, up to the order of magnitude of this power, optimal here, up to the constant c. Okay. Theorem. Kleiman and Winston. Is this the absolute constant c such that fn of C4 is at most 2 to the c extremal number. Well, extremal number is this order of magnitude. So let me just write n to the 3/2. This is the second proof we're going to see. So before proving it, let me mention a very brief briefly mention the history of this sort of counting problem. So originally Erdős asked, so some brief history. Originally Erdős asked whether Fn of h, the labeled h-free graph, number of labeled h-free graph on n equals to 2 to the 1 plus little o 1 times extremal number of h. This is quite natural. Lower bound just taking subgraph of the largest h-free graph. So basically he's saying this lower bound is correct up to an error term in the power. This turns out to be true when h is non-bipartite. So this is a result of Erdős. Frankel and Rödel says true for non-bipartite h. For bipartite graphs, no such bound is known for a single bipartite graph. But there is a counterexample. There are examples where this is not true. And there's only one example we know. It's a 6th cycle. So two counterexample. For bipartite case, this is Morrison's Sexton, who showed that Fn of C6 is bigger than 2 to the 1 plus 0, 0, how many 0? 307 times extremal number of C6. So this conjecture is false for C6, but no other graph is known. There's a similar in spirit counting results where this type of bound, when you have forbidden something, and in the power you have 1 plus little 1 times the extremal function, false is this Sidon set. This is the set with no solution to x plus y equals to u plus v. No trivial solution. Because you can take x, y, the pair equal to the pair uv. That's a trivial solution. So for this, it's also known that the number of Sidon in n subsets is at least 2 to the 1 plus some constant c, absolute constant c, times the extremal function. The extremal function is like 1 plus little 1 times square root n, something like that. Okay. It will be interesting to find one more examples where this is violated. Okay. It will be interesting to find more. For which this bound fails. Okay. Now, coming back to Kleiman-Winston, let's prove it. It's also open to prove that for any bipartite graph, we have big O of that. Also open, which is considered a difficult problem. For any bipartite H, Fn of h is at most 2 to the big O of not 1 plus little 1. We know it's not true. Big O of that. Any questions about the statement? All right. This proof is a little bit tricky, a very clever proof. So let me first say the idea of the proof. So this is the thing we want to prove. Number of C4 free graphs is 2 to the some constant times n to the 3 half. The idea is again 2 sentences if you want to summarize it. So let's try to do that. So the idea is we will think of to bound C4 free graphs. We're gonna bound it by thinking how many different ways we can build a C4 free graph from scratch, from adding vertices one by one. Okay. Now, if we can bound at every stage the number of choices to add one more vertex at every stage, then we multiply all these choices together. We would like to obtain this bound. And at every stage, when we add vertex, we're going to build auxiliary graph, which turns out to be the square of the graph. And this extension will be turned into or corresponds to an independent set in the auxiliary graph. So bounding the extension, adding each vertex to build this C4 free graph becomes bounding independent sets in certain auxiliary graph. So we bound number of C4 free graphs by bounding the number of ways to grow a C4 free graph, adding one vertex at a time. And the number of such way to add we then will use auxiliary graph which turns out gamma to be the square of the graph. So square of a graph just means if in the graph G, you have 2 vertices that are distance 2, then I add an edge. What color is good? In gamma. Okay, if they are distance 2, I add an edge. So it's possible that a pair is an edge in both G and gamma. If you have a triangle, for example. Now, why this graph? Well, roughly speaking, this, then the number, somehow in this way, the number of ways to add a vertex and maintain C4 free will correspond to the number of independent sets in gamma. Why? Let me explain this. So this is the first key point. This is because suppose this is the current graph. We grow to a certain size. Now we're going to add one more vertex. Add a new vertex. this vertex V. Okay, let's say Vi at the Vk at the k stage. Suppose currently we already have a k-1 vertex C4 free graph. Here, we're going to add one more. So how do we add? Well, we're going to choose its neighborhood somewhere here, right? And then we're going to add edges between this chosen neighborhood. We're going to decide where we add the neighbors of Vk in this k-1 vertex graph. What do we have to be careful about? We need to make sure that adding Vk does not create a copy of C4. And how to guarantee that? What would be bad would be there are two vertices here in the neighborhood, in the vertices that we decide to be neighborhood of Vk, they are of distance 2. If they are of distance 2, this is bad. No. Okay, why no? If you already have this, then you add these two edges, you get a C4. With that being said, this is saying that, and what does this mean? These two vertices cannot of distance 2. That means these two vertices cannot be adjacent in gamma. So this is an independent set in gamma. Okay, so the number of ways to add Vk is the number of independent sets we're going to add to. And this is the key thing to observe. And then, of course, we're going to use Kleiman and Winston's graph container. That will require gamma to be locally dense, supersaturation. This locally denseness basically follows, this is the second idea, so the locally denseness or supersaturation of gamma follows from two things. One is convexity, Jensen's inequality, basically. Convexity. We will see what this means. And the second thing is we're going to choose a clever ordering so that we make sure this set is not too large. So, which is a large minimum degree of this current vertex. This current graph, let me call it GK-1, say, this graph. Good. So how to make this rigorous? Let's start with the rigorous proof. Let's first make this algorithm formal. Any question with this second part is technicality. It's some calculation that I will show you how to use convexity. The key thing is to understand the first part, the algorithm, how we bound C4 free graph. So let me make it write down the details. Well, as I said, every labeled n vertex graph can be built by what? First, choose an ordering of vertices. Let's call it V1, V2, Vn. So this n vertices is an ordering of the first n integer, the labeled vertex sets. Choose your possible ordering. And now we think of growing a vertex by having V1 first and then having V2 whether adjacent or not, and then V3, and you choose the neighborhood of V3 inside the previous graph, and keep adding graph. Oh, my spectral, right? Okay, choose an ordering of this, and then start with a singleton graph G1 consists of just vertex V1, and then adding vertex for each I from 2 to n, vertices Vi to get an adding vertices Vk to get a k-vertex graph adding vertex Vk to the previous graph Gk minus 1 to get the k-vertex graph Gk, right? So you have G1, G2, G2, Gk grow to Vn, Gn. And if you want to build C4 free graph, so at every stage, every GK must be C4 free, and that's it. So if you can bound the choices of adding each vertex to grow a C4 free graph, then we can bound the number of C4 free graphs. Okay, the first thing to notice is we can bound the let's let di. We also have to fix this degree. Oh, oops. We also have to fix this degree di, a dk for the vertex bk. You fix some value, number of neighbors for it to be adjacent to. So let with degree dk to the previous graph gk minus 1 to get this k vertex graph gk. So trivially, we have what? dk is trivially at most k, right? Actually, at most k minus 1, in fact, because you are adding a vertex vk to a k minus 1 vertex graph. So at most k minus 1, in fact, whatever, I use k. So if we define g, what is parameter? gk d to be the maximum we know this added degree dk is at most k. So for every d at most k, we let gk of d to be the maximal number of ways to add a vertex of degree d to a k vertex C4 free k vertex C4 free graph, so that so let me explain what's this part about. This gk of d is basically the main function we cared about. It's basically the number of ways to add a vertex to extend to another C4 free graph. Yeah. The only thing I didn't explain is we know this vertex is at most k or k minus 1, but k minus 1 is not a good bound. It's still large. We want to make these number of neighbors we have to add to be as small as we can. And this can be achieved by a clever choice of ordering of V1 to Vn. We're going to fix to grow. This will help us to guarantee that we always add a vertex to a graph where this graph is dense, so that we can use convexity to prove the auxiliary graph is dense, locally dense. And on the other hand, we also make sure that the degree that we add, this new vertex, its degree is not very large compared to the minimum degree of G. So here, how do we achieve this purple part? That's the part I haven't mentioned. This is this is easy. We can fix ordering for any graph. We can pick an ordering. How do we pick? V1, V2 to the top to Vn, such that, let me call it U to not confuse you maybe. Such that if we call GK to be the graph induced on the first K vertices, then the minimum degree of GK minus 1, which is this graph we talk about, will be at least the degree of vertex UK in the graph GK minus 1. Why is this true? This is easy. We just always pick it from back to the front. You always pick UN to be the mean degree vertex. Now you remove it. In the remaining graph, you pick UN minus 1, which is the current minimum degree vertex. Okay, so on and so forth. So this is UK that you pick out. Then inside here, you pick a minimum degree vertex, UK minus 1. Now, why is this true? Well, look at this graph. This is GK. This is GK. Inside GK, what do we know? We know this vertex inside GK has the minimum degree. That's how we pick every time picking our minimum degree vertex. So that means the degree of this guy inside GK is at most the degree of whatever vertex here inside GK. But whatever degree here inside GK is maybe 1 plus the minimum degree of that because we remove UK in GK minus 1. Okay? Now, and that's exactly what we need. So at every time we're going to add, we choose this ordering from back to the front. Now we're going to add vertices from front to back. At every time when we add a vertex, make sure that we choose its neighborhood so that the new graph does not create a C4. And also the degree of this vertex is at most the minimum degree of the current graph plus 1. Right? The degree of this vertex that we add is at most the minimum degree of the current graph plus 1. That's what we need. Okay. So now this is well defined. Because of this, obviously, GKD for any D is at most K choose D, right? Which is bounded. And let's let GK to be the maximum over all D and most K of GK of D. Let's take the worst possible choice of D to maximize this number of extensions. After defining GK, now we can bound the number of C4 free graphs. First, choose the ordering, which is n factorial. Now choose the degree of each vertex we're going to add at every stage. The degree at every stage grows like 1, 2, 3, 4, 5 to k minus 1 at stage k. So it's another n factorial. So Fn of C4 is at most n factorial. This is ordering of V1 to Vn. Another n factorial. Degree sequence dk and most k for vertex vk times. But all this term n factorial, remember, n factorial is at most n to the n. This is like e to the n log n. E to the n log n and 2 to the bound we want is 2 to the n to the 3 half. So it is way less. This is lower order term. So what we care about is the last term times the product of the number of extensions. So gi, gk are case from 1 to n minus 1. Okay. Oh, this is probably 2 to n, sorry. Because G2 is the number of choices to add the second vertex. G3 is the maximum number of choices to add the third vertex. And Gn is number of choices to add the last vertex. So now all we need to do is to prove, suffices to show, this claim. There exists the epsilon constant C such that for any n, Gn is at most 2 to the c square root n. If this is true, every one of this term, let's just take the maximal n, which is little n here. Maybe this is confusing. Let me write capital N. Every one of this guy, capital N is at most little n, right? Let's just take the largest one. So you have 2 to the square root n, multiply n times. So that's 2 to the n 3/2. That's exactly the bound we want. Okay. This is what we need to prove now. All right. Let's do a further, let's add a further assumption, this D. We may assume this GK, this GN is realized when D is not so small. So may assume D is larger than square root n over log n. Why? Otherwise, we know Gn is trivially at most n choose D, right? Gn is, Gn is the max over all D, this guy, which is at most max over all, no. But remember, this guy is at most k choose D. So it's at most n choose D, which is En over D to the D. So this is what? E to the D log En over D. So when D is small, otherwise, if D is smaller than square root n over log n, this will imply this is smaller than E times some constant times square root n. Then we are, in this case, for this value of D, this is true. So we just need to worry about when D is large. Now let's recall, when D is large, what is this guy? So summarize what we have. Now, D is at least square root n over log n. And we have a n vertex C4 free graph, right? N vertex C4 free graph G. And we want to add a vertex V of degree D of degree dV in of degree at least D, which is at least square root n over log n, but at most, remember, delta of G plus 1. This is from this ordering. The vertex that we add is degrees at most, minimum degree of the current graph plus 1. Picture again, G, n vertex, you add a vertex V, degree D. And as I already mentioned, we cannot have two vertices at distance 2 in this graph G, otherwise we get a C4. So the neighborhoods of V in G must be an independent set in this auxiliary graph, which is square of the graph G, meaning that you make two vertices adjacent when they our distance 2. So this is an independent set in gamma. So the number of extensions of adding V to G is the same as number of independent sets in gamma of size D. Okay? Any questions so far? So now our goal is to bound this guy. So what do we know? Now what we need to do, recall, we need to show locally denseness of gamma, so we can use Kleiman-Winston. Locally denseness of gamma. This follows, as I said, we know delta of G is at least D minus 1, so the graph is dense. And we're going to use convexity. Here's what I mean. Take an arbitrary set of vertices. To prove locally denseness, let's take a set U or S, which is vertex set of gamma, same as vertex set of G. And we want to prove that there are many edges here, right? When do we have an edge? Well, we have a gamma edge in gamma if we have some vertex V with this G edge red, right? Let me say vertex W, say. So these two are of distance 2 from each other. In G, you add an edge gamma. So to prove locally denseness, let's estimate the number of edges inside some set S. The number of edges inside this auxiliary graph gamma of some set S equals to sum over all W in G, degree in G of this vertex W to the set S. Choose 2. What do I mean? Well, here, this is what I mean. If this is the neighborhood of W in S, in fact, you don't just get this single edge, you get a co-clique here. Every vertex here is of distance 2 in G through the vertex W. So you have the clique, which is this, choose 2 number of edges here. And this is equality because we don't have another vertex W prime that share every one of these hat from a W is unique. If you have another hat W prime sharing these two, that will be a C4. We know G is C4 free. So with that being said, the neighborhood of every vertex W or W prime on any set S, they can only share at most one vertex. So by taking this is edge disjoint clique. So we just add up edge disjoint cliques, which come from the neighborhood of W for all W. Does it make sense? Okay. This is from G is C4 free. Every hat, which is this W with M points in S, uniquely corresponds to an edge of gamma in S. Okay, it's a one-to-one correspondence. Now, this is where we use convexity. We have this x choose 2 function, which is convex. So Jensen's inequality, convexity. This is at least we have n vertices in our graph G. Capital N vertices in our graph G times we take the average of this degree. So it's sum over all W in V of G, degree of W in G in S divided by N. Choose 2, Jensen's inequality. Okay. How do we estimate this guy? Let's look at this sum here, average degree. So this is our S. We look at W, and that form a clique in gamma. This is the degree sum of W in S over all W. Every such edge is an edge incident to with one end in S. So this is the same as you look at the sum of all edges sending to S. It's the same as all the edges sending out from S. So it equals to the sum of all vertices V, let me call it U in S, the degree of G of U. Okay, it's the same as vertices U sending out the degree, which is at least S times, we have the minimum degree of G, right? Which is, we know minimum degree of G is at least D minus 1. Is it D minus 1, D plus 1? D minus 1. Okay. Now, look at here. We have E gamma of S at least capital N times the sum is S D minus 1 over N, choose 2. This is at least when S is at least 2N over D minus 1. You need a requirement here. This is how we're going to choose R in Kleiman-Winston. This will be at least some computation, D minus 1 square over 2N times S choose 2. Okay, and this will be our beta in Kleiman-Winston. And let me just tell you how you can choose Q. You can choose Q to be, let's say, 3 log N cube. And use the fact that D is large that we reduced to, you use Kleiman-Winston to imply that the number of independent sets of size D, that's the thing we want to bound, is at most N choose Q times capital R choose D minus Q, and some calculation, 2 to the some constant times square root N. I will skip the final calculation. All right, but so calculation is not important. Let's review the idea. The idea is counting C4 free graphs is here basically. To bound C4 free, we think of how we can grow one. We grow one by adding one vertex at a time. And we need to make sure every time when we add a vertex, we attach it to the previous graph. We don't create a C4. How do we not create a C4? Make sure that this neighborhood on top of which you're going to add this vertex does not have two vertices of degree 2, of distance 2 from each other in the current graph. Distance 2, now you build this square graph, making them adjacent when they distance 2. This will correspond to an independent set in the auxiliary graph. So bounding the number of extensions is the same as bounding independent sets in this auxiliary graph. And as we can see, this auxiliary graph is locally dense by choosing this degree sequence cleverly, this mean degree sequence, so that every time we can guarantee the minimum degree of the current graph is quite large, and the degree of this vertex is at most this minimum degree of this current graph plus 1. We don't add too many a high degree vertex. And convexity tells us that this auxiliary graph is locally dense. Any question? Okay, if there's no question, that concludes for today. Today is Thursday. I'll see you guys next week. Thanks for listening.